Welcome to Spring LIB.
For this problem, on the topic of kinematics of rigid bodies, we are shown an oil pump rig in the diagram, and we told that the link AB causes the beam BCE to oscillate as the crank revolves. Now, if we know the radius of the crank OA, and we know its constant clockwise angular velocity, we want to determine the velocity and acceleration of point D at the same instant. Now, for this problem, we'll use the following unit vectors. We'll use unit vector I to be 1 unit to the right, unit vector j to be 1 unit upward, and unit vector k to be 1 unit anti-clockwise. So let's look first at the crank OA. Now for the crank OA, we have ROA to be 0.6 meters. The angular velocity omega OA is 20 revs per minute clockwise, which we can write as 2.0944 radians per second clockwise. The linear speed or the linear velocity of VA is equal to omega OA ROA, and this is 2.0944 times 0.6, which gives us 1.25664 meters per second. That's vertically upward. The angular acceleration of the crank alpha OA is equal to 0, and so the tangential component of its acceleration, AT, is equal to 0. The normal component of its acceleration, AA subscript n, is equal to omega squared of the crank, the angular speed squared, times ROA. And we can calculate this to be 2.0944 squared times 0.6, which gives us the normal component of the acceleration of A to be 2.6319 meters per square second. And this is to the right. Now, let's concern ourselves with the rod AB. So the first thing we will do for rod AB is find the velocity VB, and VB is simply the speed VA, and the direction is vertically upward. Now VB and VA are parallel, so VA is equal to VB, and the angular speed omega AB is equal to 0, since we have straight line motion. Now VB is equal to 1.25664 meters per second vertically upward, and the acceleration of AB is equal to the acceleration of AAA plus the acceleration of B relative to A. So this is the acceleration of A plus the angular acceleration of AB times K cross with RB relative to A minus omega squared AB times R of B relative to A. So if we substitute the known values into this, we get 2.6319 I plus alpha AB K cross with 0.6 I plus 2J minus 0. And so this simplifies to 2.6319 minus 2 alpha AB times I plus 0.6 alpha AB times J. We'll call this equation 1. So we have one equation and two unknowns. Now let's look at beam BCE. And we know point C is a pivot. So we have speed VB is equal to angular speed of the beam omega BCE times R BC. And so the angular speed omega BCE is equal to VB over R BC, which is 1.25664 divided by 3, which gives us 0.41888, and that's radians per second. Now VE is equal to this angular speed omega BCE times RCE. And so this is 0.41888 multiplied by 3.3, which gives us 1.38230 meters per second. So therefore the vectors for the angular velocity of beam BCE is equal to the magnitude 0.41888 radians per second, and that's clockwise, and the linear velocity of VE is equal to the magnitude 1.38230 meters per second vertically downward. Now the acceleration of AB is equal to alpha BCE cross with R B relative to C minus omega squared of beam BCE times R of B relative to C. And so we substitute the known values into this. This becomes alpha BCE times K cross with minus 3I minus 0.41888 all squared times minus 3I. And so calculating, we get this to be 0.52638 times I minus 3 times alpha BCE times J. So we'll call this equation number 2. Now, if we equate like components of AB expressed by equations 1 and 2, then we get the following. Equating I components, we get 2.6319 minus 2 alpha AB is equal to 0.52638, which means we immediately can find alpha AB, and we get the angular acceleration alpha AB to be 1.05276 radians per square second. Equating the J components, we get 0.6 alpha AB is equal to minus 3 alpha of BCE, which means since we know alpha AB, we can find alpha BCE, and this has magnitude minus 0.21055 radians per square second. So now we have the angular acceleration of AB, alpha AB, to be 1.055276 radians per square second, and this is anti-clockwise. And the vector alpha BCE, the angular acceleration of beam BCE, is 0.21055 radians per square second, and that's clockwise. So now the acceleration of point E is equal to the acceleration of E relative to C in the tangential component plus the acceleration of E relative to C in the normal component. Now, the acceleration of A, or of E rather, relative to C, the tangential component, is equal to alpha BCE crossed with R of E relative to C, and this is equal to minus 0.21055 K cross with 3.3 I. So this gives us minus 0.69482 meters per square second times J. Now, for ED, we have for string ED, we have VD is equal to VE, which is 1.382 meters per second vertically downward, which is the first answer we were looking for. And then AD, we said, is A of E relative to C. That's the tangential component, which we calculated to be 0.695 meters per square second vertically downward.